Question 3 shows a velocity time graph for a ball that's bouncing vertically. The first question, just testing your knowledge, what does the gradient of a velocity time graph represent? If you don't know that at this stage, you better go and read the book, read your notes, do some revision and find out what it means. But as a clue, the gradient of a velocity time graph, the gradient is always going to be the change in something, so it's the change in velocity divided by the time. So hopefully you know what that means. Next part, explain why the gradient of the line CD is the same as line AB. Well, if you've worked out what the gradient represents, and then you ask why is that gradient the same as that gradient, presumably it must be because the thing that it represents is the same. Part 3, what does the area between the line AB and the time axis represent? So the area under a velocity time graph. Again, no point me telling you that, so you've got to, if you don't know it yet, you better go and learn it. What does the area under a velocity time graph represent? Part 4, state why the velocity at C is negative. So what's it for? It's a velocity time graph for a vertically bouncing ball, which is released at A, strikes the floor at B, and then what does it do? But when a ball bounces, it strikes the floor, what happens next? If you know what happens next, that will explain why the velocity at C is going to be negative. State why the speed at C is less than the speed at B. So it hits the floor, it rebounds. After it's bounced, it's got less of something, and having less of this thing means it's also going to be going slower. Part B tells you the mass of the ball, it tells you the initial height. After impact, the ball rebounds to a height of 0.75 meters. So calculate the speed of the ball immediately before impact. I can think of two ways of doing this that will both give the same answer. You could either do it by thinking about energy. If it's falling, it's losing a certain type of energy and gaining another type of energy. And since the question right at the start says we can ignore air resistance, we can assume that the energy it loses by falling is equal to the energy it gains by speeding up. Alternatively, you could do the question by SUVAT. For the last part, again you could do it by energy, because you know after it's bounced, you know how high it gets, so therefore you know how much potential energy it's got to gain. So that tells you how much kinetic energy it must have had just after the impact. So that's one way of doing it. Or the other way is again, do it by using SUVAT. We know how far it travels. We know that when it gets to the top, it's not moving anymore. So you can use the SUVAT equations to work out how fast it must have been going as it left the surface. Question 4. In a vehicle impact, a car ran into the back of a lorry. The car driver sustained serious injuries which would have been much less had the car been fitted with a driver's airbag. So the first thing you're asked is to explain why the effect of the impact on the driver would have been much less if an airbag had been fitted and had inflated in the crash. So this question really, it's your chance to show that you understand the ideas involved in acceleration and force. So you can assume that the injuries the driver sustains are caused by big forces acting on him. So if you can explain why there were big forces on him and relate that to his acceleration and what acceleration means, and then explain that if they had an airbag, what difference that would have made to the way in which he came to rest, and therefore to his acceleration, and therefore to the force that were acting on him. Part B, calculate the deceleration of the car if it was travelling at a speed of 18 meters per second when the impact occurred and was brought to rest in a distance of 2.5 meters. So we know the question is about deceleration, which of course just means acceleration, and we expect it to be negative, so it's slowing down. We've got an initial speed, we know it's brought to rest, that tells us the final speed, and we know how far the driver travels while this is happening, so that's got SUVAT written all over it. So start out by writing SUVAT and then choosing the right equation to work out the acceleration. Question 5 is about a spacecraft initially moving straight up the page towards A at 890 meters per second. To change course, a sideways force is produced by firing thrusters there, which increases the velocity sideways towards B from 0 to 60 meters per second in 25 seconds. And it tells you the mass of the spacecraft. It asks you to calculate the acceleration towards B. If you look at the question, remember that acceleration is a vector, so just like force, so we can treat the acceleration in the direction towards B completely separate from the acceleration in the direction towards A. So it tells us some information there about how the velocity changes. It gives us initial velocity and a final velocity and how long it takes. So there's enough information there for us to calculate the acceleration towards B. Next part, find the force on the spacecraft produced by the thrusters. Well, what does the force do? The force gives it the acceleration that you just calculated. So how do you work out how much force is needed to give a certain acceleration? Well, the question tells you the mass, doesn't it? So that's going to have something to do with it. Got the mass and the acceleration. How do we find the force? Part B, calculate the magnitude of the resultant velocity after 25 seconds. Well, we know that after 25 seconds, we know that it's moving towards B at 60 meters per second. But that's not the resultant velocity, because all the time this was happening, it was always moving at 890 meters per second in the direction towards A. So to find the resultant velocity, what have we got? We've got 890, and we've also got this one we just calculated, this one we've been working with, of 60. So the spacecraft's got both those velocities, 890 in that direction, 60 in that direction. So what's its actual resultant velocity? We'll just add them together as vectors. Whatever answer that gives is your answer. And the final part, calculate the angle between the initial and final directions of travel. Well, we've just worked out the final direction of travel. What was the initial direction of travel? It was straight up the page. So what's the angle you're looking for? Work that one out. Got enough information there to find that angle.